What we'll do here is to show an example, the application of a probability distribution function to actual data. For this, we'll use the Salvezza River data that was presented in lecture. First part of the lecture notes showed data for the Salvezza River from 1895 to 1916. Those data were plotted up as a histogram. Alright, so what we're going to do here is to show how we might analyze those data in the form of a probability distribution function. And that probability distribution function can then be used to evaluate some design, or to formulate some design questions. Okay, so what we'll be doing here is looking at both the Excel spreadsheet and also a Word document that I'll write on the blank pages, write some formulas. You can see in this Excel spreadsheet, and I will be posting this Excel spreadsheet so that you'll have access to it. Excel spreadsheet has the data on the left hand side. Column A, you've got the year of the flow measurement. Column B, we have the actual flow measurement, and these data go from 1895 to 1916. Given in row 24 and 25 are the mean and standard deviation of the data. The mean flow is 66,204 cubic feet per second, and standard deviation is 19,046.5 cubic feet per second. The CV there is what's defined as being the coefficient of variation, and it's just the ratio of the standard deviation to the mean, and the coefficient of variation is 0.287. The quantity mean of y and sigma of y are the mean and standard deviation for the logarithms, natural logarithm of the values of the flows. So each of the values of the flows, you take the logarithm and then you calculate the mean and the standard deviation in the same way that we did it for the values of x, that is the untransformed data. You can see that the mean of logarithm of y's is 11, and the standard deviation of the logarithm of y is 0.28. When we start off here, we talked about cumulative, or we talked about probability function, a cumulative probability function, as being the integral underneath the probability density function. And here we'll look at this. We say that the probability density function is just p of x. That's a small p. Whereas the cumulative probability distribution function is some x less than or equal to some, we'll call it x1. So if the x distribution is given by this, let's say it has a shape like this, doesn't have to be a bell-shaped curve. We would take a value of x1 and we'd find the area to the left here, and remember the area under the whole curve is equal to 1.0. The area to the left of the x1 is something less than 1, and so this is just that area. If I were to plot p of x less than or equal to x1 versus x, we get a S-shaped curve that I talked about before, with the maximum value being 1.0. Now what I'm going to do is to show you how to derive this function just from the data without any concern about whether it's a normal distribution, an exponential distribution, or whatever. We've already shown a histogram for the data, where we broke the data up into class intervals and plotted the relative frequency of occurrence of individual values within a given class interval. We could use that to derive this cumulative distribution function. I'm going to show you a different way to do it, and that is, we're going to use an empirical formula. It says that P of x less than or equal to x1 is going to be given by the formula R1 divided by m plus 1. Here R1 is the rank that a particular value has in a sorting of the data. We take the data and we sort them from smallest to largest, regardless of which year it occurs in. Sample them, or to arrange them from smallest to largest. The rank would be the value, or would be the R would be the rank of a particular value in that arrangement, and capital M is the number of values that you have. So let's look at our Excel spreadsheet. In here we've got the flows given by the years in which they occurred, and then if I were to sort those from smallest to largest, you'll see that column C has them arranged in that way. The smallest value in column B is 34,700, and the largest value is 115,000. There are 22 values in total. The rank goes from 1 to 22. So 34,700 is the smallest value. 46,100 is the second largest. So these numbers in row D or column D are the rank numbers, the R1s that I talked about before. Now if I take those values in column D and divide them by m plus 1, here m is equal to 22, so m plus 1 is 23. If I divide those by 23, these numbers in column E are those values, and those correspond to the probability that x is greater than x1. Here I call it q greater than equal to q sub t, where q is the discharge and q sub t is some particular discharge associated with, or the particular discharge associated with the ranking number. So in column E we're saying that the probability that in any given draw, that is in any given year, that the Q will be greater than 34,700, the value that's associated with that rank, is just 1 divided by 23. Well, 1 divided by 23 is 0.043. For the second rank number, 46,100, we divide 2 by 23. That has a probability of exceedance. Q greater than or equal to QT means exceedance is 0.086. If we look at the largest one, 115,000, we're saying that the probability of Q being greater than 115,000 is about 95%, or 95.6%. Now, I won't concern us right now with the RP, which is called return period. For right now, we'll just leave that off at this point. And actually, the numbers that are in column F are not even correct. What we should have done there, right now I've got the wrong formula for that, and these numbers would actually reverse. The one in row 1 would be 1.045, and the one in row 23 would be the 23.0. But for right now, I won't concern myself with that. And maybe I should go ahead and correct that right now. So this will be just the quantity (1 minus I'm going to take a break here just a second while I fix this. Okay, so I have the RP values fixed now. So the smallest value, the smallest rank value, has a return period RP of 1.045, and the return period of the largest value is 23 years. But for right now, we won't look into that any further. So now if I were to take and plot the value of X, that is the flow in column C, against the probability of exceedance of that value, I get the curve that you see to the right. It's the empirical, what we call the empirical model. Those red dots are the individual values. And actually, there's another mistake here. This is the probability, not of exceedance, but the probability of non-exceedance. That is the probability that value is less than the QT. So, okay. So this plot here, this Salvisa River, Kentucky plot, which has the probability that Q is less than QT versus the individual discharge, has this these red dotted or plotted red points. Kind of looks like a S-curve. If you were to sketch through that set of points, it would have the shape of an S-curve, ideally. Now, how do we then use this? Well, we could work directly from this curve or these data to then interpolate individual values of probability. I could go into that graph, choose any discharge, and I can find out what the probability of that the Q will be less than that value directly from the graph. But it's of interest to engineers and other scientists that we might want to be able to try to fit a theoretical graph or function to those data. One of those functions would be, for instance, the normal distribution. Another one might be the log normal distribution. And as a third example, we could maybe use the exponential distribution function, which is discussed as a very simple function in the slides, the lecture slides. So what I'm going to do is show you how to derive the theoretical values that will then plot on top of a graph like the one that's shown here. To plot the theoretical graph, we create a column just with a set of points or a set of values of discharge, and we can let that cover quite a range. Maybe a range even larger than the range of the actual data. The actual data went from 34,700 cubic feet per second to 115,000. Here I've created a range from 10 to the minus 5, essentially 0, out to 190,000 cubic feet per second. So that column P goes all the way down to 190,000, as you can see here. Now what's nice is that Excel makes it very easy for you to calculate the probability that Q will be less than Q sub t for the theoretical model. Here I'm going to be using the log normal distribution, which is shown in the notes, the class notes for this topic. And it's very easy to use Excel to do that. And here I'm looking at the second row in column Q. This is the argument that you use, lognorm.dist, that is the log normal distribution, for the value of P2, which is the discharge that I'm interested in. The arguments are B27, and B28, and then the word true. If I put true in there, it will calculate the cumulative distribution underneath the exponential function. So the exponential function is small p of x, or small p of q, and we want the capital P of q. If I put true in, it will give me the area under the curve to the left of the value of P2, or the value of q. The B27 and the B28 that you see there are the mean and the standard deviation of the logarithm of the flows that were in the data set. As I mentioned before, those were shown down here. So in column B, row 27 and row 28, we had the mean and the standard deviation of the logarithms of the values of q. And those are the values, two values that are used in each of these rows of column Q. We just substitute those in, and we can see that as the discharge increases, the probability that Q will be less than the value of Q given in the column B, or column P, increases. And it increases to the point where when I get to 190,000, we're pretty close to 100%, or 1.0, for the probability of the Q being less than that value. Here we'll just ignore the column R and the column S because we really don't need to use those at this point. Now if I were to take the value of the Q in column P and I plot them against the value of P in column Q, it'll give me a graph which is essentially the same type of data as what we just plotted in the previous graph. And here we'll see superimposed then we have the empirical model that we had in the graph immediately above by the red dots, and then the blue squares are the values of Q plotted against P for the log normal distribution. And we can see here that is the numbers in columns P and column Q. We can see here that the theoretical distribution, the log normal distribution, does a pretty good job of describing the relationship between the probability of Q being less than some value of Q, T, against the actual value of the discharge. We would say here that the log normal distribution does represent the data that was collected quite well. And if we wanted to, we could calculate from that theoretical distribution the probability for any discharge value. Just as a comparison to this, let's look at another function, another probability distribution function, the exponential distribution, which is discussed in the lecture notes. For the exponential distribution, the probability function, probability density function, P of x is equal to a e to the minus ax. And of course, the probability that x is less than or equal to any x1 is just going to be equal to the integral P of x dx. And if I can get down to the next line, which I don't seem to be able to do here. I'll just take another break here while I get this fixed. Here we go. Alright, so the integral capital P of x less than or equal to x1 equal to the integral from 0 to capital X1 or to x1 of a e to the minus ax dx is just going to be equal to 1 minus e to the minus ax1. That's the cumulative distribution for the exponential function. And so the exponential function has this kind of shape. P of x versus x is like this. And the cumulative distribution function, capital P versus x, is of course going to have this sort of shape to it. So of course this P that we have here is the area, that is P of x less than or equal to x1 is the area to the left of the line. And something happened to my plot there. That'll come up something like that. So I can use this equation here in the Excel spreadsheet to calculate the values of the probability. And it turns out, as given in the notes, the mean or the value of a for the exponential distribution, this a that you see in the formula, is just 1 over the mean, which is just 1 over x bar, the value of x that we, or from the values of discharge that we calculate, we get the mean value, and we take the inverse of that, and that's the value of a. So that's a fairly simple function to evaluate. I don't need anything special from Excel to do that. I just substitute in, put in the formula 1 minus exponential of minus 1 over b24 times the value of P2, where P2 is the selected value of discharge I want to evaluate the function for. The B24 from the bottom of the spreadsheet on the left-hand side was the mean of the sampled values of Q. Alright, so now if I plot these values of Q versus the values of U here, I get the plot of the exponential distribution. We still have our same, what I call the empirical model, given by the red dots, and the exponential function then is given by the blue squares. And we can see that that function does not fit the data very well at all. So I'll just give you an idea that, well, theoretical distribution functions are important. They can be very useful, but you need to be careful as to which one you choose to work with your data. In this case, the log normal distribution fits the data very well. The exponential distribution does not fit it very well. There could be other cases, other types of data where we'd find just the opposite effect, or the opposite result, where the log normal distribution would not be a very good fit, and the exponential distribution would be a very good fit.